For this first problem, I need to interpret what it's asking. The symbol d dx stands for taking the derivative. And in order to compute the derivative, I need to remember the power rule, which says if I want to compute the derivative formula for a power of x, my variable, then you identify the power, represented in the symbol as n. You take that power, multiply x, and you reduce the power of x by 1. So for example, if I want to take the derivative formula for x to the fourth, my power is 4, and so the new power will be 3, and my derivative formula will be 4x cubed. Now, as I use that formula for the formula that's been given, the derivative formula for x to the fourth is 4x cubed. And then I want to subtract 3 times the derivative of the formula of the derivative for x cubed, which is 3x squared. Then I want to take 5 times the derivative formula for x squared, which is 2x. The derivative of 8x will be 8, and constants don't have any derivatives. So as I find my final derivative formula, I get 4x cubed minus 9x squared plus 10x plus 8. And that's the derivative formula of the function that was given. Now some observations. I didn't want my formula to be isolated, so I created an equal sign that said, when you find the derivative formula of this polynomial, it's equal to this new formula that I have. And when I simplified it again, I said the previous formula is equal to my new formula. Now an alternative way of writing this problem, if I wanted to write it down, would be to define a function. And notice that the function that I've defined matches the formula that's inside the brackets. And then I would say, when I compute the derivative function, so I create a new function f prime of x, I get a new formula, 4x cubed minus 9x squared plus 10x plus 8. But one thing I do not do is I never say that this function f of x equals its derivative. For our second problem, we're given a function. So we're told f of x equals x to the fifth minus 3x cubed plus 3. And we're asked to compute some quantity that's written df over dx with a bar and a 2 at the bottom. So we need to interpret this. We're given a function, and this symbol represents the slope or rate of change of that function at 2. So this rate of change is found, the rate of change at 2 is found using the derivative, evaluated at 2. So in order to solve this problem, we need to first compute the derivative. Using the power rule, I can identify each term, x to the fifth, x cubed, and the constant, and I'm able to calculate the derivative of each piece. So my f prime function, the derivative function, can be found as 5x to the fourth minus 3 times 3x squared, and the constant term, its derivative would be 0, so I get a formula 5x to the fourth minus 9x squared. Again, some key facts. I don't want to have this formula isolated, so I identify it as my f prime function equals the formula. And as I simplify the formula, again, I want to have an equal sign. In order to find the slope or the rate of change at 2, I need to evaluate this function at 2. So my rate of change at 2 is the value of my function at 2, which I can evaluate using my formula 5 times 2 to the fourth minus 9 times 2 squared. 5 times 16 minus 9 times 4, which is 44. And so I found the rate of change of my function at 2. For this problem, I'm given the formula for a function, and I'm asked to find the equation of the tangent line of the graph of that function, y equals f of x, at x equals 2. So what are the steps? To find the equation of a line, I need a point and a slope. And if I have a point and a slope, then the equation of the line can be found as y minus the y value of the point is the slope times x minus the x value of the point. For my problem, I'm given the x value, so I'm told that x equals 2. So to find the point, I need to use my function. And so if I put 2 into my function, 2 cubed gives me 8, minus 2 times 4, the 8's cancel, so I get plus 2 minus 5. My y value is negative 3. And so my point, AB, is the point 2, negative 3. Now to find my slope, I'll use the rate of change, or the derivative. My slope will be the rate of change of my function at 2, or in other words, the value of the derivative function at 2. So I need to calculate my derivative. F prime of x will be equal to 3x squared, so equals 3x squared minus 4x plus 1. And so when I plug in my x equals 2, f prime of 2 will be 3 times 4, or 3 times 2 squared, minus 4 times 2 plus 1, for a value of, let's see, 12 minus 8 is 4 plus 1 is 5. So my slope is 5, which allows me to write down the equation of my tangent line. Y minus the y value is the slope times x minus the x value. In other words, y plus 3 equals 5 times x minus 2. And that's the equation of my line in point-slope form. That's what I'd be looking for. If I need to solve for y, I just add or subtract the negative 3 to the other side. Negative 3 plus 5 times x minus 2, which is just as good. The next problem gives me a polynomial and asks what are all the possible integer roots. And so this problem is an application of the integer root theorem. My polynomial has coefficients that are all integers. And so when I want to find the integer roots, they all have to be factors of the number negative 30. So I start looking at factors for negative 30. The factors of 30 are 1 times 30, 2 times 15, 3 times 10, 4 doesn't go into it, 5 does, 5 times 6, and that's as far as I can go. So my possible integer roots are these 8 numbers and their opposites. And so the possible integer roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. Now how would I go about finding which ones are? Well, one way would be to graph my original function and just see if the graph crosses. Or I could plug each of these values into the function and see if I get 0. Or I could use synthetic division. And in this class, if I asked you to verify, I'd actually want you to show me using synthetic division that it worked. So although it's not actually assigned for this problem, let's illustrate the point. Let's do a test, and let's check both plus or minus 1 to see if they're roots. So let's check plus 1 first. I write down the coefficients of my polynomial. Then I put down the test root, start with a 0, and then I go down, I add, I multiply by 1, I add, I multiply by 1, I add, I multiply by 1, I add, multiply by 1, I add, and I get a remainder. The final number is my remainder, and so in this example, f of 1 equals 0, and I found a root. If I was to check negative 1, I would repeat the process. I'd write down all the coefficients, I'd leave space for the second row, put down my test number, negative 1, repeat the process. I add, multiply by negative 1, I add, multiply by negative 1, add, multiply by negative 1, I add, let's see, that gives me 18, multiply by negative 1, and add, I get 12. My remainder is 12, and that tells me that my function value at negative 1 has a value of 12. And so this is not a root. Question 5 is a conceptual question related to our previous example. If I have a polynomial, and I know that f of 3 equals 4, if I were to do synthetic division, the value 4 would be the remainder. So the idea is, if I have f of x, and I were to divide it by the factor coming from this test point, x minus 3, I would get a quotient of some sort of polynomial, q of x, and I would get a remainder, r. And the division algorithm says my polynomial is x minus 3 times this quotient polynomial that I don't know, plus the remainder. So that if I plug in 3, I get 3 minus 3, which is 0, times something else that I don't know what it is. But 0 times that is 0, plus my remainder. My function value at 3 is the remainder. And so the concept that this question is wanting to make sure you understand is that when you do division, the remainder is the value of the function. And so this is all you're expected to understand in the answer to that question. Problem 6 puts together all the ideas we had in the previous problems. I start by having a polynomial, and because all of the coefficients are integers, all I need to do is look at the last term, which is a negative 4, and I can identify possible integer roots. These integer roots are all of the integer factors of the number 4. So we get plus or minus 1, plus or minus 2, and plus or minus 4. And I test those using synthetic division. Now if you have a graphing calculator, it's faster to graph the polynomial and see where the roots most likely look like they occur. So let's go through the process. We'll do it with synthetic division entirely. I start by writing down my coefficients. So 1, minus 1, minus 2, 6, and minus 4. And let's test the root at negative 1, possible root at negative 1. So I just quickly go through my addition. My synthetic division tells me that negative 1 is not a root. not a root because my remainder was not equal 0. So now we'll do it again. Let's test the next possible root, -1, -2, 6, -4. I want to test the root at 1. So I repeat the process again. Add, multiply, add, multiply, add, multiply, add, multiply, add. My remainder is 0, so I have found a root. And this gives me one factor out of my polynomial. What I've discovered is my function, and notice I'm creating an equation, is a factor x minus 1 coming from my root times another polynomial which gives me x cubed, and the reason it's cubed is I have constants, x's, x squareds, and x cubed. X cubed, there are 0x squareds minus 2x and plus 4. So I have one of my factors. I need to now use the cubic. So I'm going to now factor this deflated polynomial and just look at x cubed minus 2x plus 4. And again, I have the same possible roots. And my coefficients are 1, 0, -2, 4. 1, 0, -2, 4. I've already tested -1 and it didn't work to start with. 1 worked once. Let's see if it works again. So I add, multiply, add, multiply, add, multiply, and add. So 1 is not a root of the deflated polynomial. So let's check -2. 1, 0, -2, 4. Check -2. And multiply -2, 4, 2, -4, 0. Wow, okay, I found the second root. So what I found is that x plus 2 is another factor. So I keep my first one, x minus 1. I have a new one, x plus 2, which is x minus -2, times a quadratic, x squared minus 2x plus 2. And now all that's left is to think about the roots. I need to see if this quadratic has any additional roots. And so I can solve that using the quadratic formula. X squared minus 2x plus 2 equals 0 has roots when x equals -b plus or minus square root b squared, that's 4, b squared minus 4ac, 4 times 2 times 1 is minus 8, all over 2a. And when I simplify that, 2 plus or minus square root of -4 over 2, I don't have any real solutions, so this has no real roots. And I've identified all of my roots. There are two roots. There's a root at 1 and a root at -2. So my roots are x equals 1 and x equals -2. Problem 7 is based on knowing that you've already solved problem 6. And so we are going to take this function g of x, which is the square root of a polynomial, and the polynomial we're looking at is the polynomial from the previous problem. So the domain of my function g, the domain of g, is the set of all input values x. So what could go wrong? Well, the polynomial itself never has any problems, but a square root has a problem if it's negative inside. So we want to solve when is this polynomial x to the 4th minus x cubed minus 2x squared plus 6x minus 4 we need to know when it's greater than or equal to 0. And in the previous problem, we found all of the roots. So in a typical problem, you might be expected to be given at this point a polynomial, and you would need to first do the steps we did in problem 6 to find the factors of that inside polynomial. Once I know the factors of that polynomial and all of the roots, I can do sign analysis. So I can mark down all of the places where my function inside the square root is 0. So I take my polynomial, I have a root at 1 and a root at -2, and there were no other roots. And so now I can pick values and see what signs I get. So for example, if I pick a number greater than 1, like 2, this factor will be positive, second factor will be positive, and this third factor, the quadratic, if I pick 2, I get 4 minus 4 is 0 plus 2, that's positive. So I get 3 positive values. Well, because this quadratic doesn't have any real roots, this will always be a positive factor. So if I pick a number between -2 and 1, like 0, I get a negative and a positive, and the quadratic's positive, so I get negative. And if I pick a number like -3, I get negative, and the quadratic's still positive, so 2 negatives makes positive. The inequality I needed in my domain, I needed to see where this polynomial was greater than or equal to 0. And so I can find the domain of G now. The domain of G is going to be the interval from -infinity to -2, including 2 because that's where it's equal 0. We skip everything between -2 and 1, and then I create a union of the interval from 1 to infinity. That would be my domain.